In a delta-delta transformer configuration, there is no inherent neutral point, meaning the system itself is not grounded by default. Corner grounding is a specific technique used to ground a delta system. It involves connecting one of the phase corners of the secondary side directly to a grounding electrode. For the transformer setup, consider these connection recommendations. On the primary side, connect directly to the 480 volts breaker located within the 480 volts panel. On the secondary side, the connections are as follows. Firstly, connect zone, typically identified as red, to the A phase of the 240 volts fuse disconnect. Secondly, connect X2, generally marked as yellow, to the B phase of the 240 volts fuse disconnect. Thirdly, connect X3, commonly labeled as blue, to the C phase of the 240 volts fuse disconnect. The X4 terminal, often orange in color, should not be connected. This terminal represents the neutral point, which is not utilized in a delta-delta transformer configuration. Regarding system grounding, since there are no 120 volts loads in the system, grounding is not strictly required. However, it's highly recommended for safety reasons. If implementing system grounding, connect the X0 terminal, if present on the transformer, to a grounding electrode. Note that the X0 terminal is not present on this particular transformer. In terms of bonding, ensure the transformer frame is bonded to the grounding electrode. Additionally, install a bonding jumper between the fuse disconnect enclosure and the transformer frame. Several additional notes are important. Verify the fuse disconnect is rated for 240 volts and possesses an adequate interrupting capacity. Always refer to local electrical codes and regulations for specific grounding requirements that may apply. If the decision is made to ground the system but the transformer lacks an X0 terminal, an external grounding transformer or a connection to a ground rod will be necessary. Expanding on the concepts, it's crucial to understand the purpose of grounding and bonding in electrical systems. Grounding provides a low impedance path for fault currents to return to the source, allowing overcurrent protection devices like circuit breakers or fuses to operate and clear the fault. This helps to prevent electrical shock hazards and minimizes equipment damage. Bonding, on the other hand, ensures that all metallic parts of the electrical system are at the same electrical potential. This eliminates voltage differences between metallic components, further reducing the risk of electric shock. When dealing with a delta-delta transformer, the absence of a neutral point necessitates careful consideration of grounding methods. Corner grounding, while a valid option, can introduce some complexities. For instance, the entire system voltage is present between the ungrounded phases and ground. This can increase stress on insulation and require equipment with higher voltage ratings. Another option is to create a neutral point artificially using a grounding transformer, also known as a zigzag transformer. This transformer has a special winding configuration that provides a low impedance path to ground for zero sequence currents, effectively establishing a neutral point for grounding purposes. If choosing to use a grounding transformer, ensure it is properly sized to handle the expected fault currents. The size of the grounding electrode conductor should also be selected based on the grounding transformer's capacity. Proper selection of overcurrent protection is also critical. The circuit breaker or fuses protecting the transformer should be sized according to the transformer's rated current and in accordance with the National Electrical Code, specifically Article 450. Additionally, the interrupting rating of the overcurrent protection devices must be sufficient to handle the available fault current at the transformer's secondary terminals. The available fault current can be calculated using a point-to-point method or by using available fault current calculators. In the absence of 120 volts loads, the primary concern is to protect the 240 volts equipment and personnel from ground faults. By implementing a solid grounding system, any ground fault will result in a high fault current, causing the overcurrent protection devices to trip and to energize the circuit. The grounding electrode system should consist of a grounding electrode conductor connected to a suitable grounding electrode. Acceptable grounding electrodes include metal underground water pipes, metal frames of buildings, concrete encased electrodes, ground rings, and ground rods. The size of the grounding electrode conductor depends on the size of the service entrance conductors or the derived system conductors. Refer to NEC Table 250.66 for the appropriate conductor size. It is also essential to ensure the impedance of the grounding path is low enough to facilitate the flow of fault current. This can be achieved by using appropriately sized conductors and making sure all connections are clean and tight. Regular inspection and testing of the grounding system are also recommended to verify its effectiveness. Ground resistance testing can be performed using a ground resistance tester to ensure the grounding electrode system is providing a low impedance path to ground. In addition to grounding and bonding, surge protection should also be considered, especially in areas prone to lightning strikes or voltage transients. Surge protective devices, or SPDs, can help protect sensitive electronic equipment from damage caused by voltage surges. SPD should be installed at the service entrance and at downstream panels to provide comprehensive surge protection. When working with electrical systems, always follow safe work practices. To energize the circuit before working on it, use appropriate personal protective equipment, and verify the circuit is energized using a voltage tester. If you are not qualified to work on electrical systems, consult with a licensed electrician. Understanding the specific requirements for grounding and bonding a delta-delta transformer is crucial for ensuring a safe and reliable electrical system. By following the recommendations and guidelines outlined and consulting with qualified professionals, the risk of electrical hazards can be minimized. Remember that electrical codes and regulations can vary depending on the location, so it's always important to consult with local authorities and qualified electricians to ensure compliance. In summary, for a 480 volts to 240 volts delta-delta transformer supplying a 240 volts and CC section with no 120 volts loads, firstly, connect the primary to the 480 volts panel. Secondly, connect the secondary phases zone X2 and X3 to the fuse disconnect. Thirdly, leave X4 unconnected. Fourthly, bond the transformer frame and fuse disconnect enclosure. Fifthly, consider grounding the system via an external grounding transformer or ground rod for enhanced safety. Sixthly, always adhere to local electrical codes and regulations. Finally, prioritize safe work practices and consult with qualified professionals when necessary. To further elaborate on the concept of fault current, it's important to understand how it flows in a grounded system. In a properly grounded system, when a fault occurs, that is, when an unintentional connection occurs between a phase conductor and ground or a metallic enclosure, a large fault current will flow through the grounding path back to the source. This high fault current will then trip the overcurrent protection device, such as a circuit breaker or fuse, quickly disconnecting the circuit and preventing further damage or injury. The magnitude of the fault current depends on several factors, including the source voltage, the impedance of the fault path, and the impedance of the source transformer. The lower the impedance of the fault path, the higher the fault current will be. Therefore, it is crucial to maintain a low impedance grounding path to ensure that fault currents are high enough to quickly trip the overcurrent protection device. This is achieved by using appropriately sized grounding conductors, making sure all connections are clean and tight, and minimizing the length of the grounding path. In ungrounded systems, such as a delta system with no intentional ground, a single ground fault will not result in a large fault current. Instead, the system voltage will shift, and all ungrounded conductors will be elevated to the full line to ground voltage. This can create a dangerous situation, as a second ground fault on a different phase will then result in a phase-to-phase fault, which can cause significant damage. For this reason, it is generally recommended to ground delta systems, even if there are no neutral loads. Grounding the system provides a defined path for fault currents to flow, allowing overcurrent protection devices to operate and clear the fault. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. Article 250 of the NEC covers grounding and bonding requirements for all types of electrical systems, including delta systems. The NEC specifies the types of grounding electrodes that are permitted, the size of grounding conductors, and the methods for bonding metallic enclosures. It is essential to follow the NEC requirements when designing and installing electrical systems to ensure safety and compliance. When selecting a grounding electrode, it is important to consider the soil conditions at the site. The soil resistivity can affect the performance of the grounding electrode. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable, as it allows for a lower impedance grounding path. If the soil resistivity is high, it may be necessary to use multiple grounding electrodes or to improve the soil conductivity by adding chemicals such as ground enhancement material. Ground enhancement material is a conductive material that is added to the soil to improve its conductivity. It typically consists of a mixture of minerals and chemicals that help to reduce the soil resistivity. Ground enhancement material can be used to improve the performance of grounding electrodes in areas with high soil resistivity. Another important consideration when grounding electrical systems is the potential for ground loops. A ground loop occurs when there are multiple paths to ground, creating a circulating current in the grounding system. Ground loops can cause noise and interference in sensitive electronic equipment, and they can also create a shock hazard. To prevent ground loops, it is important to ensure that there is only one path to ground for each piece of equipment. This can be achieved by using isolated ground receptacles and by avoiding the use of multiple grounding electrodes that are connected together. Isolated ground receptacles have a separate grounding conductor that is isolated from the building's grounding system. This helps to prevent ground loops by providing a dedicated grounding path for sensitive electronic equipment. In addition to grounding and bonding, surge protection is also an important aspect of electrical system protection. Voltage surges can be caused by lightning strikes, switching operations, and other disturbances. Voltage surges can damage sensitive electronic equipment, and they can also create a fire hazard. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges. SPD are installed in parallel with the electrical equipment that they are protecting. When a voltage surge occurs, the SPD diverts the surge current to ground, protecting the equipment from damage. SPD are available in a variety of voltage ratings and surge current capacities. The appropriate SPD for a particular application depends on the voltage level of the system and the expected surge current. It is important to install SPD at the service entrance and at downstream panels to provide comprehensive surge protection for the entire electrical system. When working with electrical systems, it is always important to follow safe work practices. To energize the circuit before working on it, use appropriate personal protective equipment and verify the circuit is energized using a voltage tester. If you are not qualified to work on electrical systems, consult with a licensed electrician. It's paramount to understand that the information provided is for educational purposes and does not substitute professional engineering advice. Electrical systems are complex, and any work performed on them should be done by qualified and licensed professionals. Incorrect grounding and bonding practices can lead to serious injury or death. Always consult with a qualified electrician or engineer before making any changes to an electrical system. The concepts of system grounding and equipment grounding are distinct but interconnected. System grounding refers to the intentional connection of a current-carrying conductor, typically the neutral, to ground. This establishes a reference point for the system voltage and helps to limit voltage surges. Equipment grounding, on the other hand, refers to the connection of non-current carrying metallic parts of equipment, such as enclosures and frames, to ground. This provides a low impedance path for fault currents to flow, allowing overcurrent protection devices to operate. Both system grounding and equipment grounding are essential for electrical safety. In a delta-delta transformer configuration, the system is not inherently grounded, as there is no neutral point. However, it is still necessary to provide equipment grounding for all metallic enclosures and frames. This is achieved by bonding the enclosures and frames to a grounding electrode system. The grounding electrode system should consist of a grounding electrode conductor connected to a suitable grounding electrode, such as a metal underground water pipe, a metal frame of a building, or a ground rod. The size of the grounding electrode conductor depends on the size of the service entrance conductors or the derived system conductors. Refer to NEC Table 250.66 for the appropriate conductor size. In some cases, it may be desirable to ground the delta system even if there are no neutral loads. This can be achieved by using a grounding transformer, also known as a zigzag transformer. The grounding transformer creates an artificial neutral point, which can then be connected to ground. Grounding the delta system provides a defined path for fault currents to flow, allowing overcurrent protection devices to operate and clear the fault. It also helps to limit voltage surges and reduce the risk of electrical shock. When selecting a grounding transformer, it is important to consider the size of the transformer and the expected fault current. The grounding transformer should be sized to handle the maximum available fault current. The grounding electrode conductor should also be sized based on the grounding transformer's capacity. The NEC provides detailed requirements for grounding transformers in Article 450. When installing a grounding transformer, it is important to follow the manufacturer's instructions and the requirements of the NEC. The grounding transformer should be located as close as possible to the source of the power. The grounding electrode conductor should be connected to a suitable grounding electrode. All connections should be clean and tight. Regular inspection and testing of the grounding system are also recommended to verify its effectiveness. Ground resistance testing can be performed using a ground resistance tester to ensure the grounding electrode system is providing a low impedance path to ground. In addition to grounding and bonding, surge protection should also be considered, especially in areas prone to lightning strikes or voltage transients. Surge protective devices, or SPDs, can help protect sensitive electronic equipment from damage caused by voltage surges. SPD should be installed at the service entrance and at downstream panels to provide comprehensive surge protection. When working with electrical systems, always follow safe work practices. Energize the circuit before working on it, use appropriate personal protective equipment, and verify the circuit is energized using a voltage tester. If you are not qualified to work on electrical systems, consult with a licensed electrician. Understanding the specific requirements for grounding and bonding a delta-delta transformer is crucial for ensuring a safe and reliable electrical system. By following the recommendations and guidelines outlined and consulting with qualified professionals, the risk of electrical hazards can be minimized. Remember that electrical codes and regulations can vary depending on the location, so it's always important to consult with local authorities and qualified electricians to ensure compliance. Furthermore, consider the implications of using a high-resistance grounding system versus a low-resistance grounding system. High-resistance grounding limits the ground fault current to a low value, typically 10 amps or less. This can reduce the risk of arc flash and equipment damage, but it also makes it more difficult to detect ground faults. Low-resistance grounding, on the other hand, allows for a higher ground fault current, typically several hundred amps. This makes it easier to detect ground faults, but it also increases the risk of arc flash and equipment damage. The choice between high-resistance grounding and low-resistance grounding depends on the specific application and the priorities of the user. If arc flash mitigation is a primary concern, high-resistance grounding may be the better option. If ground fault detection is a primary concern, low-resistance grounding may be the better option. Regardless of the grounding method chosen, it is essential to follow the requirements of the NEC and to consult with qualified professionals to ensure a safe and reliable electrical system. In conclusion, properly grounding and bonding a 480 volts to 240 volts delta-delta transformer is essential for safety and reliable operation. By following the recommendations and guidelines outlined, consulting with qualified professionals, and adhering to local electrical codes and regulations, the risk of electrical hazards can be minimized. Always prioritize safe work practices and never attempt to work on electrical systems if you are not qualified.